The last time we discussed the properties of charge and the methods of charging, namely charging by rubbing or friction, and the other one charging by induction, that is without contact. Now this time we are going to solve a few basic numericals about properties of charge, and then we will discuss the Coulomb's law. Before we discuss the Coulomb's law or we solve the numericals, first of all we are going to write down a few important values that we have to use often in electrostatics. These are the mass and the charge of electron and the proton. So here is the mass of electron. I am using the symbols M for mass, E for electron. So the mass of the electron is 9.1 into 10 raised to minus 31 kg. Okay, it's very small again. Now the charge on the electron, Q is the symbol of charge, E is the symbol for electron. So the charge on the electron is minus 1.6 into 10 raised to minus 19 Coulomb. Again, remember that Coulomb is the SI unit of this. Coulomb is the SI unit of charge. Okay, so don't forget that Coulomb is the SI unit of charge. Now okay, so this is all about electron. Now for proton, so the mass of proton, MP, P for proton again, is 1.67 into 10 raised to minus 27 kg. So you can notice that it's actually much higher compared to that of an electron. In fact, we have mass of proton is about 1846 times the mass of electron. Okay, so the proton is actually very heavy compared to the electron. Now the last thing, that is the charge of proton. So the charge of proton is, well, same as that of an electron in magnitude, but they have different polarities. That is, the charge of the proton is positive 1.6 into 10 raised to minus 19 Coulomb. Okay, so these are the four important values that we should know, because we have to use them frequently in electrostatics problems. Now we're going over to solve a few numericals. So let's get started. First of all, we are going to solve the example 1.2. So it says if 10 raised to 9 electrons move out of a body to another body. So let's say that there are two different bodies. Okay, so here's the first one and here's the other one. Okay, from body 1 to body 2, electrons are moving. Okay, and they are moving at a rate of 10 raised to 9 in 1 second. Okay, so 10 raised to 9 electrons are leaving the body 1 and entering the body 2 in 1 second. Now we have to find how much time is required to get a total charge of 1 Coulomb on the other body. So gradually, as the electrons will move from body 1 to body 2, there will be more and more charge developed on body 2, right? So we have to find out the time in which the total charge on the body 2 will become equal to 1 Coulomb. Okay, so that is, in what time will the total charge on the body 2 become 1 Coulomb. You should not forget that here we are assuming that at start the body 2 was neutral, that is, it had no charge, and now gradually, as more and more electrons will enter the body 2, the body 2 will become negative. Okay, so when will the charge become minus 1 Coulomb? Again, minus sign is only indicating the polarity. Okay, So that's it. That's for understanding the question. Now we want to solve this one. So this is how we're going to do it. See, first of all, I'm going to think that in 1 second how much charge is flowing out into from body 1 and into body 2, right? So it's that in 1 second the charge flowing out should be, well, 10 raised to 9 electrons go, okay, and each of them carries a charge 1.6 into 10 raised to minus 19 Coulomb. So this is the charge flowing out in 1 second, okay, right? Because one electron takes 1.6 into 10 raised to minus 19 Coulomb with it, and there are 10 raised to 9 electrons going in 1 second. Okay, now what we have to do is we have to find the time t, okay, so we don't know the time t in which the charge over here developed on the body 2 is going to be 1 Coulomb. So all you have to do to solve this problem is just a simple cross multiplication. I'm leaving that part for you, so that will give you the answer as t is something sometime in seconds, right? And just by looking at these numbers I can say that the answer is going to be actually very huge because of the powers involved over here. So whatever it is, later on you could convert it to bigger units like days or hours or seconds or whatever, years or anything. Okay, so that's it for this example 1.2. I hope you are going to complete it on your own. Okay, now that we are done with this example 1.2, we are going over to the Coulomb's law. But before we go to the Coulomb's law, I want to assign you a bit of practice problems. Okay, so I want you to solve example 1.3 on your own, and also exercise questions 1.11, that's 11, okay, on your own, right? Now when you solve this example 1.3, it's talking about a cup of water, right? Now a cup of water actually could have any amount of water, so I want you to take 250 grams of water for the calculation. Okay, right? It's not specified very clearly in the question, the textbook, what is the amount of water, so we'll have to guess something and we will take it to be 250 grams of water. Okay, so these are two problems that I want you to solve before we proceed on to the Coulomb's law. I hope you solved those two problems, and now we are ready to discuss the Coulomb's law. So you are going to find that Coulomb's law is equivalent of the Newton's law of gravitation. Okay, so just like the Newton's law of gravitation caters to the gravitational field and the gravitational force and all that, just in the same manner the Coulomb's law caters to the electric force between two objects and all that. Okay, so first of all we are going to talk about the Coulomb's law in the scalar form. Okay, so we'll only worry about the magnitude of the force, not the direction. So let's start. So let's say that suppose that there is one charge over here, Q1, okay, and here is one more charge over here, Q2, and let's say that these two, they are point charges. Okay, so remember that Coulomb's law works or is applicable only when these charges are point charges. So let's say there are 2 point charges, but these 2 point charges, they are separated from each other by a distance r, and there is vacuum over here, there's space over here, there's no gas or nothing else, right? So then according to Coulomb's law, the force that acts between these two charged particles, its magnitude, the force magnitude acting between these two charged particles or point charges, is directly proportional to Q1 into Q2. See, this is just like you had the Newton's law of gravitation, which was F is proportional to m1 into m2, right? So well, we have the same thing here, though I have to tell you that I have to make a small change here. It is that we should write modulus over here because of the fact that charges may be negative, right? We have considered that there are two kinds of charges, either positive or negative. So because magnitude can't be negative, we must put a modulus over here. And then the next part about the distance, I'm sure you remember that even gravitational force depends on distance. Well, just like that, the electrostatic force or Coulombian force between two objects or 2 point charges is directly proportional to 1 upon r square. Okay, it is proportional to 1 upon r square. So we can say that here, well, the Newton's law of gravitation and the Coulomb's law are identical in that aspect, that here too you have F is proportional to 1 by r square. So what you could basically say is that both of these laws, they are inverse square laws. Okay, so inverse square laws because both the forces, they are proportional to the inverse of the square of the distance between the two particles. Okay, so that's what we have for Coulomb's law, and you can see the similarities with the Newton's law of gravitation. Right now, just like for the gravitational force between two objects, when we remove these proportionality signs from here and from here, right, we ultimately have to write a constant. So ultimately, for gravitation, we write the gravitational force is equal to m1 m2 on r square, right? And here I have to write a constant, and that constant is g, which is universal gravitational constant. Now just like that, for electric force or electrostatic force between 2 point charges, we write that the force is q1 into q2 divided by r square. Well, no surprises so far, and like I said, you should put these two in a modulus, and then I have to write a constant here, and that constant is k, right? This k is called the Coulomb's constant. Okay, k is called the Coulomb's constant. Right now, obviously, just like g has a value, k should also have a value, and the value of k in SI units is 9 into 10 raised to 9. So very nice value, easy to remember. 9 into 10 raised to 9 in SI units, which are actually Newton meter square per Coulomb square, right? Okay, that's also not difficult to figure out. We get the units easily from this equation at the top. So this is the basic and the very important formula of the Coulomb's law, right? So in words, I'm not going to write it in words, I'll just say it. It's very simple. If you have this equation in mind, it's very easy to say it. It is that the electrostatic force acting between two charged particles, remember point charges. Okay, so electrostatic force acting between 2 point charges in vacuum is directly proportional to the magnitude of product of those charges. Okay, that is F proportional to q1 q2 in a modulus. So the force acting between these 2 point charges is directly proportional to the product the magnitude of the product of the charges, and inversely proportional to the square of the distance between them, as you can see over here, right? It is inversely proportional to the square of the distance between the 2 point charges. So that's about the Coulomb's law. And before we wind up, here's one more thing that I have to tell you. Well, many books, and generally people do tend to write a value of k in form of some other physical constant, which is called electrical permittivity of free space. Okay, so well, there is a way to write K, and which is as follows. K is written as equal to 1 upon 4 pi epsilon 0. Okay, so what I've written over here is K is 1 upon 4 pi epsilon 0. That's how you could also write the Coulomb's law, by putting this value in place of K. What is this weird symbol? Well, let me elaborate that. Let me tell you about what's that symbol here for. Okay, so that symbol is epsilon 0. Okay, so this is how you read it: EPSILON, epsilon. Okay, so that symbol is epsilon, and 0 or O for vacuum. So this epsilon stands for electrical permittivity. Oh, excuse me, bad place to write. You won't be able to see when the text goes behind. Okay, so we have, this is epsilon again, and it is called electrical permittivity. Okay, permittivity is referring to some kind of permission, but we will talk about electrical permittivity in the second chapter. Okay, so I'm just telling you the name. So it's called electrical permittivity, and it's 0, so that is, I mean, value is not 0, but we are writing this 0 here. O, that stands for vacuum, so we say that this is electrical permittivity of free space. Okay, it is electrical permittivity of free space, right? So I've told you K's value. Now I want you to find out on your own what is the value of this epsilon 0, and also find out the units. Okay, so that part is for you to do on your own. All you have to do is plug it in this equation and you'll get your answer. Be lazy, make sure you do it. Now that we are done with the Coulomb's law in scalar form, we are going to talk about its vector form, okay, which is also very simple to understand. Well, so first of all, let me put the title over here. So let's say Coulomb's law, and this time we are going to talk about its vector form. Now we have already discussed about the magnitude. It is F is equal to K into modulus Q1 Q2 upon R square. So now what remains is to talk about the direction, because a force is a vector, and a vector is made up of two components, or two parts really. One, the magnitude, and second, the direction. Okay, so let me draw a nice diagram over here so that we can get started with the explanation. Okay, so let's say that this is some coordinate system, and with an origin O over here, right, and that there are 2 point charges, let's say one over here, right, and one more over here. So let's call this Q1 and let's call this Q2. So there are 2 point charges, Q1 and Q2, and now we are going to draw their position vectors. So position vector of the first one will be from origin to the first charge, and of the second one will be from origin to the second charge. So I have to label this one, it's called R1 vector, right, and this other one, the second one for the second charge, should be R2 vector. Now I want you to think about the direction in which charge 1 gets a force from charge 2, right? So I can say that we are talking about force on charge 1 due to or by charge 2. So we are talking about force on the charge 1 due to charge 2, and I'm sure you remember these symbols. The symbol of this force would be F12 vector, force on charge 1 due to charge 2. Okay, so well, for simplicity right now, let's assume that both of these charges, Q1 and Q2, they are positive. Okay, right, for simplicity, let's assume that both of these charges are positive. So in that case, the magnitude of this force can easily be written as K Q1 Q2 upon R square, where R stands for distance between these. I'll come to that point very shortly. Okay, so this is what we have to write. You may have noticed I'm not putting the modulus because both charges are positive, so there's no need to put the magnitude or the modulus sign. So this is the magnitude of the force on 1 due to the second charge, that is F12 is K Q1 Q2 by R square. Now we want to talk about direction, and we have said that both of these are positively charged. That means they are going to repel, correct? So because they repel, the force on 1 due to 2 will be in this direction, which is exactly the opposite direction, in from where this charge 2 lies. That's because of the fact that the charge is repelled. So what Q2 is going to do is it's going to push Q1 away. So this vector that I've drawn here indicates the F12 vector, right? So now I should specify a way to write or note the direction of this vector, F12 vector. So how can I do that? Well, what I'm going to think is I can see that this vector is just in the same direction as this vector is. Alright, that's interesting. Okay, I hope you noted that the green vector, okay, and the F12 vector, they are in the same direction. So I can actually say that if I want to write the direction over here, okay, see, we have written the magnitude. Okay, this is the magnitude, but we don't know what's the direction. So when we want to write the direction, I can actually write the direction of that green vector. So what's that green vector? Try to recall it from your 11th standard physics. It's a very basic thing about vectors. What's that green vector? Look at the diagram carefully. What do you think is that green vector? Okay, I hope you got it. The green vector is R1 vector minus R2 vector, correct? So the green vector is R1 vector minus R2 vector, and that means the direction of F12 vector is same as direction of R1 vector minus R2 vector. So that's what I should be writing here in the direction. Okay, so what shall I write? Well, I'm going to write this. So this is the direction of that F12 vector, that is the force on 1 due to charge 2. Now some of you may have got it, okay, what R12 hat means, but let me still explain it so that everyone understands it very well. Okay, so I'm going to keep the diagram here and I'm going to erase what I've written so far. Okay, okay, fine, let me just write it over here below the diagram at this place. It's going to be convenient for everyone to see it. Well, see, this is how it works. I hope you remember that in relative velocity concepts we have learned that R12 vector, if we want to write R12 vector, we should write it as R1 vector minus R2 vector, just like relative velocity equations are written. Okay, so R12 vector is R1 vector minus R2 vector, right? But if I do not put the usual arrow sign, instead of that I put the hat, then that means we are talking about unit vector, which indicates direction. So what I've written over here is that magnitude of this F12 vector is k q1 q2 by r square, okay, and the direction of that vector is same direction as r12 vector, that is r12 vector and f12 vector, they are in the same direction, correct. I'm just going to make a minor change here so that our equation is very clear to anyone who reads it, and that minor change is I don't know what happened here. Yeah, so it should be that I should write r12 over here. Okay, so if I write r12, that means we're talking about distance between 1 and 2, or we are talking about the magnitude of the r12 vector. Okay, so this clearly indicates that when we want to find out the force between charge 1 and charge 2, then we should use the distance between the charge 1 and 2, obviously, nothing else, right. So this is all that we have for Coulomb's law in vector form. You might have a question, what if these charges were negative, or what if one of them was negative but the other was positive? Well, even in that case, the expression that we have derived works correctly, because what happens is, if one of the charges is negative, right, if one of the charges is negative, then you are going to notice, you are going to see that this term, let's say q2 is negative, then this term q2 will be negative, okay, right. So that means that the direction of f12 should get reversed, correct. So the direction of f12 vector should get reversed. Well, that is correct, because if one charge is positive, q1 is positive, and q2 is negative, in that case the force between these two charges is not repulsive, but the force is attractive. Okay, so the f12 vector arrow will be reversed, it will be in the opposite direction, not away from q2 but instead towards q2. Okay, so in that case, automatically the fact that q2 is negative will take care of the attraction instead of repulsion. So that means there's no need to change even if q2 is negative, right. And say similarly, if both would be negative, q1 q2 both are negative, the same thing would happen. Two negatives would ultimately lead to positive, right, because negative into negative gives you positive. So ultimately the direction of f12 vector will be same, that is repulsive, right. So what this means is, even if charges are positive or negative, doesn't matter, one law in the vector form works for everything. Okay, so I'm going to summarize what we have studied, and I'm just going to write the Coulomb's law in scalar and vector forms again for you, so that you can remember it very easily, because there are many problems that we have to solve based on Coulomb's law. Okay, so let me clear this up and I'll write everything again. Okay, so well, this is what we have studied, that if there are 2 point charges, then the magnitude of the Coulombian force between them is F is equal to k q1 q2 by r square, or even better r12 square, right, if the distance between these two is r12. Okay, so that's what we have in the scalar form. And if you want to write the same thing in vector form, all you have to do is put a arrow, all right, and put r12 hat. So now this will give you the direction and the magnitude both of the force acting on the first charge q1 due to the second charge q2. instead, if you want to find out what is F21 vector, that is force acting on the second charge due to the first charge, well, then I'm sure you have guessed, it's very easy. It's that it should be F is Q2 Q1 into K upon R21 square, right? So it's going to be R21 hat as well. So what we have is that all you have to do is you have to replace or interchange the charges 1 and 2. But this leads you again to a very interesting observation. Well, do you see that the magnitudes are going to be same? That is, I can call the distance between these two charges either as R12 or R21. There's no difference, right? The distance is still the same. Distance of 2 from 1 is same as distance of 1 from 2. But the difference between these two forces is here in the directions. You can see that one is R12 hat and the other is R21 hat. Okay, so R12 hat is from 2 to 1, correct? You can recall it, you can see it again by rewinding this or going a bit backward in the video. And R21 hat is from 1 to 2, right? So the only thing that has changed between these two is the direction. In fact, it has reversed, right? Okay, so that means I can easily write that F12 vector is negative of F21 vector. Well, that shouldn't be a surprise for anyone because we have already studied Newton's law and we have been talking about it for so long. So again, you can see that the Coulomb's law actually satisfies the Newton's law, third law. Okay, so it says that the force is acting between 1 and 2, the charges 1 and 2, they are opposite in directions but they are equal in magnitudes, right? So that's all really for the Coulomb's law, and we are done with the theory now. We're done with the explanation. Now we are going over to solve some basic problems about Coulomb's law from the ticket. Okay, so now that we are done with the Coulomb's law in both the scalar and the vector form, and we have seen that it's quite similar to the Newton's law of gravitation, to solidify your concepts, we are going to solve the example 1.4. okay, and then I'm going to assign you a few problems to do on your own. Okay, so I'm reading the question here. Coulomb's law for electrostatic force between 2 point charges and Newton's law for gravitational force between two stationary point masses both have inverse square dependence on the distance between the charges and masses respectively. Well, obviously yes, like I said, the relation is quite similar. Just like F is proportional to m1 m2 by r square in Newton's law of gravitation, you have F is proportional to q1 q2 by r square in Coulomb's law. Okay, so further the question reads: A, compare the strength of these forces, that is the Coulombian force and the gravitational force, by determining the ratio of their magnitudes, 1 for an electron and a proton and 2 for two protons. Okay, so what we have to do is we have to compare the strength of these forces, that is we have to find the ratio of the Coulombian force or force due to charges, okay, and the gravitational force, okay, Fg. So we have to find out the ratio of these two forces. For what? Well, in part A, remember we are doing part A of this problem. Again, there are two subparts. Well, the first one is you have to find this ratio for a proton and an electron. That is, what this means is that you have, okay, Okay, well, this is a proton here, okay, P, and here is an electron, okay, is negative. You have to find what is the ratio of Fc, that is Coulombian force, and the gravitational force between these two point charges. Okay, so the idea is fairly simple. All you have to do is to put these values, okay, in the formula that we have studied, and that's all, right? So let's begin with it. Okay, so I'm going to clear this up. Okay, I hope you have understood what the question is, so I'll get some more space, right? Okay, so first of all, as we put these values, these formula here, Fc upon Fg is equal to, well, the formula of Fc, Coulombian force between 2 point charges, is K. See, we are only interested in magnitude, right, into modulus of first charge proton. Its charge is plus E. I hope you remember that the charge of the proton, or the magnitude of charge of electron, is E, and the second one is electron's charge, so into minus E, right? But anyways, we are going to put a modulus, so if you want a shortcut, you could not write the minus sign and just go straight away with it. And now divided by r square, but this is only for the Coulomb's force, and now we have to divide this whole thing by gravitational force, which is G mp, because mass of proton and the mass of electron, they are not same, don't forget. Okay, and then again divided by r square. I'm sure you have already understood how to handle this situation. All we have to do is cancel r square, right? That's very easy to do. Okay, isn't it? We will cancel r square, and now what remains is we have to put the values of these constants, right? So k's value 9 into 10 raised to 9, e into e square, where e's value is charge of the electron magnitude, so that is 1.6 into 10 raised to minus 31, and then square it, right? And then G stands for universal gravitational constant, and that's all you have to do really, and you will get your answer. Okay, I'm just going to tell you that you should expect that the answer is pretty big. Okay, it's very big. It's going to be lots of powers of 10, right? 10 raised to also a big number here, right? So what I mean to say is, this is going to show us that the Coulombian force is going to be much greater than the gravitational force, and that's not a surprise, because very early in your 11th standard we have talked about the 4 fundamental forces, and well, we said that out of the 4 fundamental forces, gravitational force is the weakest force, right? And the electromagnetic force is much stronger compared to the gravitational force. So this is going to give you an idea. This calculation will allow you to explore that the difference, the magnitude difference between the Coulombian force and the gravitational force. Okay, well, in the same context, I want to tell you one thing. Say that you lift an object. Let's say this is an object and I'm lifting it. Okay, you can clearly notice that the earth is going to make it fall down, right, because of gravitational force, and my hand is trying to stop it from falling down. And well, who's the winner? Well, my hand is the winner. My hand succeeds. It can stop this book from falling down, correct? Well, that force between the book and the hand which stops it from falling down is the normal force, correct? But what you should understand is that at the heart of this, at the base of it, the normal force is actually due to electromagnetic forces or electric forces between charges inside our body, that's my hand, and the book. Okay, so what is happening is that the whole mass of Earth, huge object, Earth, the planet, the entire planet is trying to attract this book, move this book down, right? But it's up against just this. Okay, 5 fingers, that's it, and a palm. So the force applied by my hand, it's so strong, right, compared to the force applied by the entire earth. So that is what indicates the comparison or the magnitude differences between the Coulombian force and gravitational force. Okay, so hopefully you will understand the importance of Coulombian force now, or the force between charges, right? Every time I say Coulombian force, it actually means the force between two stationary charges. Okay, so I hope you realize what kind of role it is playing, right? Even frictional force is due to Coulombian force, right? So that indicates that all these things, the charges and the forces between them, they are like really important for us. We wouldn't even be able to walk, or I wouldn't be able to sit on this chair that I'm doing right now, okay, or I wouldn't be able to use this laptop over here and make a video to show it to you. So there are so many things that depend on the forces between charges, right? So I hope you will keep that in mind, right? So before I finish this topic of Coulomb's law, I'd like you to I'd like to insist that you solve a few problems, right, from the book. First of all, you finish the example. Make sure you finish the example 1.4. Okay, we have left it incomplete. We have only done part A's 1. Okay, there are more to be done, but I'm leaving that to you because I think you will be able to handle it easily. Okay, so that will give you some practice. So you have to do example 1.4. you have to finish it, okay, right? And then I want okay, fine. So that's really it. That there's no more for this topic that I can assign you. Okay, so that's it for Coulomb's law. Make sure you remember it. F is proportional to Q1 Q2 by R square, okay, or F is equal to K Q1 Q2 by R square. Okay, that's the magnitude. And in vector form, F12 vector is K Q1 Q2 upon R12 square, R12 hat. Alright,